Oh, oh. Hi, my name's Chad. I go by Chadtech and I'm Slack and online. In this talk, I'm going to talk about hash maps.
We're going to go through like the algorithm of a hash map, kind of my experience in having to implement a hash map for a really cool programming language called Rock. If you haven't heard of it, check it out. It's kind of like Elm. It's very fast. It's functional. It's got a lot of exciting things I can't get into right now, but check it out if you can. Anyway, so this talk is about hash maps. So right off the bat, in Elm, we don't have a hash map type. We don't have a hash map at all, but we do have a dictionary type, which just kind of feels the same way. You know, like it's a collection of things that you look up by a key, so you're inserting values by key and you're getting values out. I've got like an example right here of users. So you might have a users dictionary where you're looking up users by their name or their ID or something like that. You know, looking things up and putting them back in. Hash maps are the same way in that it's like a collection of things that you're looking up by key and inserting by key. Other languages actually just have something called hash map. So like Rust has a hash map type. I think Haskell's map type is probably a hash map. A hash map is like an implementation of this kind of thing. And we're going to just talk through that implementation. Like how does it work? So one note about why I'm giving this talk. I just thought it was really interesting, and I didn't know this stuff before I had to implement it. And I didn't go to school for computer science, right? So if I don't go out of my way to learn this stuff, I'm just going to sit in my natural state of not knowing it. So maybe you're like me, and I can kind of get you up to my level pretty quickly. On the other hand, I gave this talk before, and part of the audience were like a lot of very old and experienced, like computer science kind of programmers who've been doing this forever. They went to school for it. And their response was like, yeah, this is what a hash map is. No duh. Okay. So just want to let you know what you're in for. Totally welcome to watch this talk, of course. But yeah, let's jump into it. If I had to say most directly what a hash map is in its implementation, remember we're talking about the implementation. Hash maps are like arrays in that you have like internally, like how a hash map works. You have like a list of elements and you look them up by index, just like an array. But the trick is in the API, you got a key and you turn the key into an index. Right, so I guess the name of the game regarding hash maps is how do you go from some arbitrary key to a number that you could look up in the array. So we need to convert some data that is the key and convert it into a number, which will be the index. And we need to do that in a way that will work when we put things in and when we get things out, kind of get the same value, right? So we turn a key into an index by means of a hash function. Yeah, so a hash function, maybe you already know what the hash function is, but a hash function takes something, or it takes anything really, and then it gives you a number. And then the number is unique to the input. So my name's Chad. If you put Chad in the hash function, maybe you get 2 out. Right, choose a number. Then every time I put in Chad, I always get 2. Someone else might get 2 as well. So there could be collisions, right? So two distinct inputs might get the same output. But the point is that the output is consistent to the input. And the collisions are the edge cases anyway. So getting 2 inputs that get the same output is not the norm. Oh, and just to be detailed here, because it's going to matter later, hash functions also take a seed. So you put in the input, maybe it's a name like Chad, and then you give it a seed, and then you get an output, and it's the same output per the seed and per the name. So okay, I've written a type alias here to kind of represent what that means. So a hash map, it's kind of parameterizing over a key and a value, but really just internally, it's just an array of positions that have that key and value. I've made up this type called a slot. Let's kind of take a look at it. So a slot can either be an entry, in which case we store the key and the value, or it can be empty, or it can be this third type called a tombstone, and we'll get into that later. Just forget about it. So I guess another true thing about hash maps, like another true accurate description of a hash map, is that a hash map is an array that can have holes in it. Right? So if you have an array that's 4 long, there's 4 elements in there, right? Because all 4 slots are necessarily filled, right? There's something there. But hashmap doesn't have that property where it's not continuous, right? If it's for long, kind of confusing, but if it's for long, many of those spots might be empty. Just for is actually like a description of its memory size, and not really its description of like how many elements are inside of it. Okay, a little bit more context, and then we'll be in the substance of this talk. Yeah, there's two important ingredients. One is the hash function, which I just talked about, and another one is this kind of made up arbitrary number I'm going to call a level size. And for the purpose of this talk, a level size is 4. Now in practice, you'd probably use a larger number, but I'm trying to explain it to you. So a level size is 4. A level size is kind of like, so you'll see once we get into the implementation, but hash maps have to kind of grow and shrink in their size. And a level size is how much is it going to grow by when we choose to grow it. So hash maps start off just empty. They just start off as nothing. And then when you put something in, you can't just put the first element into the first position. You have to grow it to an arbitrary size and then put your first element somewhere in that size, and then you've inserted it. Kind of confusing, right? You need to create space and then put your first element somewhere in that space. So there's necessarily like a lot of emptiness around the first element. It'll make more sense. Okay, so now we're in like the substance of this talk. Let's talk through like a hash map that takes people's names and it stores their favorite color. Right, so the key is a name, a string name, and then the value is a color. So we're going to start with an empty hash map, which I've represented here as just like an empty list. Not to be taken literally, it's not actually a list, I'm just trying to demonstrate it. So we've got an empty hash map, nothing in it, and we've got this color type. So let's add let's add yellow under Chad, under the key Chad. So take my name, Chad, we're going to hash it, we get 2, meaning we want to put the key value Chad yellow at index 2 of our hash map. Now we have a problem immediately, which is our hash map is empty, which means there's no index 2, right? It's length 0, there's no index in it. So the first thing we need to do is we need to allocate enough space for index 2 to even exist. A level size is 4, so we go from like an empty array to an array of 4 empty slots. Right? We grew it by 1 level size, now it's 4. Now index 2 does exist. So now there's enough space to insert Chad yellow. So this is what the hash map looks like at this point. Right? It's just 3 empty slots and then 1 entry. Now let's add Becky's favorite color. So Becky's favorite color is olive drab. Let's hash the key Becky. Suppose Becky comes out to a hash of 1. Our hash map becomes this, right? So now there's 2 entries. Becky's in position 1. I'm in position 2. And then there's 2 empty slots. No problem. We didn't have to allocate anything because there's already enough space. So now let's add the color red under the key Walter. So Walter's favorite color is red. Suppose Walter's name hashes to 2. Now we have another problem, right? So my name hashed to 2. Walter's name also hashes to 2. We have what's called a collision. Taking the first step, both of our names want to go to the same index. This is a problem, right? Because we can't both be in this spot. This is the essence of hash map stuff. Is how to deal with the collisions in a way that will make everything all make sense at the end of the day. Since index 2 is already taken up in our size 4 hash map, we're just going to expand it and make another level, right? So we're going to put on 4 more empty slots at the end. So we're going to go from 4 to 8. So our second level in this hash map is, indices 4 to 7. Right? Do I have? Yeah, 4 to 7. And once we know that we have to go to the next level because there's a collision in the first level, then we rehash Walter. Remember I mentioned that seed in the hash function? So say I'll summarize all this. I'm sorry if it's confusing, but in the first level, maybe the seed was 0. Then we hit the collision. So then we go to the next level. We rehash Walter, but now the seed will increment the seed. Right? The seed's 1. So we rehash Walter, and we get our new index, which is the size of the first level plus the new index, and then we have our new slot, which is empty because we just added all these new empty slots. So it's 4 plus 0, index 4, that's where we're storing Walter's favorite color. So we resolve the conflict by just kind of making more space and then putting Walter in that new space. So now let's do something different. We've been inserting values. Let's get a value out. So suppose we want to retrieve Walter's favorite color from the hash map. So we hash Walter, we get the index 2, we go to 2, and we pull that value out, and it's not Walter's favorite color, it's my favorite color, because I'm in position 2, right? But we can check that the key at position 2, which is Chad, is not the same as Walter, which is what we're looking for. So we know that this is not the value we were looking for. There might have been a collision. We need to look in the next level. So this is how the algorithm works. It just goes level by level, doing the hash, seeing if the key at that spot matches the one we're looking for. So yeah, so there's a collision. We need to rehash for the next level. We get the index 0. Walter hashes to 0 in the next level. And so 4 plus 0 is 4. Then we look at that entry, and sure enough, there's an entry there, and the key there is in fact Walter. So we got the value we wanted. We found it. And we can return that value. Okay, let's do something different again. Let's delete my favorite color. Suppose I don't want to be associated with this favorite color stuff anymore. I want to pull my data out of the product. I want to export my data. So we need to delete my favorite color from the hash map. Right, just going through the steps. We hash my name, which is 2. Then we go to index 2 in the hash map. We look at the key. It is Chad. So now we can delete that entry. We do something special here. Remember that tombstone thing? When we delete an entry, we actually just put tombstone there. We don't switch it to empty. We put tombstone. And this is important because remember how we had a collision between Chad and Walter at that point? Well, if we just switched it to empty, then when looking up Walter, you might just get to empty and then think like, oh, Walter's not here. That would be false, right? Walter is there, it's just at the next level. So you need some indicator that there's nothing here now, but there was, and since there was something there, there could have been a collision, and you need to keep looking for the value we want. Okay, so new thing, next step. Suppose we want to look at Katarina's favorite color. Katarina is absent from the hash map. We never inserted her favorite color. We hash map Katarina to 0 and look up that slot and find empty. Okay, so it's empty. Right? We know Katarina is never an entry here. We don't return anything. We return nothing or something from the hash map. So one fact about the hash map is reaching an empty slot terminates the algorithm, right? If you reach an empty slot, you know that the value is just not there. So if Katarina hashes to 1 instead, we would go to the first index, which is where Becky's value is. Compare Katarina to Becky, not the same. So we know that if Katarina is in this hash map, we need to go to the next level. We would go to the next level, find an empty slot. There, we know Katarina is not in the hash map. If Katarina hashes to 2 instead, we look up index 2, we find a tombstone. So we didn't find Katarina, but we also know that Katarina might still be in this hash map, right? Just in another level. So then we have to go to the next level and do the whole thing over again. And we would find empty, right? Because Katarina was never in here. It's not in the first level, not in the second level. Just absent. Yeah, that's it. Thanks so much for watching my talk. Yeah, I want to give 2 shout-outs real quick. One is to the Rock programming language, where I got to learn all this cool stuff because I implemented hashmap for that language. Check it out if you can. Yeah, second shout-out I want to make to where I work. So I work at a really cool company called Construction Site, kind of like Construction Site without the con. We make a really cool project management product for the construction industry. So like managing the state of a building as it's getting built. We do things in Elm and Rust. We've even got Rust on the front end, which is really cool. If that excites you, you want to work with me and my cool coworkers, just reach out to me. Maybe we can figure something out. So I'm going to do some supplemental things. Things that would have been like more advanced that I didn't really want to cover in the main talk because they would have just prolonged things and confused things. But now that you've been through the main talk, maybe I can tell you this stuff and you'll find it interesting as well. So yeah, the level size in this talk was 4, which is a small number, right? I think in practice you'd probably want to do something like closer to 1,000. I'm not really sure, but there's no single correct answer because there's like a performance trade-off with doing one or the other. So if you have a very large level size, you're like guaranteed to have like a large minimal size of the hash map, right? So if your level size is 1,000, then it's necessarily going to be at least 1,000 big in your memory. If you've allocated one level, so you have necessarily bigger data in memory for doing that. On the other hand, if you do a small level size, you're probably going to have to reallocate more often, right? You're going to have more collisions, which means you're going to have to, like, in the computer's memory, it's going to have to grow and shrink more, which takes time. Having collisions will, like, slow down lookup speed because you have to go through each level and kind of checking keys and then moving on. That takes time. So the speed is hurt by having a small level size. And that's what I want to say about level sizes. Oh yeah, and hash maps. So something I left out is like cleaning up hash maps. Hash maps. So if you notice, like, you could have two hash maps which in theory are equivalent because they have the same keys and values, but they're not equivalent in that they have, one has tombstones that the other one doesn't. One is like, one's way longer than the other as an array. So that highlights some interesting things about computers, where, like, if two things are equal, like that's something that has to be defined in some way. I think it's like higher level languages, kind of like Elm. It seems weird that equality would be like a type class or a property, but when you get to this lower level stuff, two things which, as people think about it, are identical, in memory they're not identical. But you know that in practice they really should be identical, so you need to actually implement how are you going to determine if they're identical. Yeah, so that's just a thing that's interesting. There's also a problem where hash maps only grow and they never shrink, unless you've implemented something that will deliberately shrink them. But then you need to do that, right? Because if insertion only includes the possibility of growing the hash map, and deleting elements only puts tombstones in the space that was allocated, they never actually shrink. They're just going to grow and grow and grow over time. So you could have some kind of strategy for doing that. Like maybe after you delete something, then after you delete an element, you check if there's more elements after that are just empty spots, and then you just cut the tails off every time you do a deletion. That's one strategy to doing that. But it's kind of interesting because then deleting is like necessarily a more costly thing than inserting. You have like this cleanup step that sometimes happens. So say you had like a computer, you had a hash map running on your computer, and you're kind of inserting and deleting and doing all that stuff. Every now and then you'd get this like pause where it's just cleaning up, and it wouldn't really be like, it'd be a very discrete segment of time that would happen sporadically whenever you choose to implement your kind of cleanup step.